Yeah. So the next topic that we'll be continuing with the previous class is about the Euler's operation. So yes, we have to make use of certain operations to modify the solid modeling that we are doing, because always so what we do is that when we create the solid modeling, uh, uh, let it be solid modeling or even 2D drawing or wireframe, what are the type of modeling frame that we're going to use, there is always that there is going to be some kind of modifications that we are going to do. So we are going to alter it with compared to its initial state, right? So then what happens? So there is going to be some change in the either the vertices or the number of edges or the number of faces. So some changes is going to happen because the operator or the user is going to do these actions, right? Okay, so subsequently, when we do certain changes, so either the vertices or edges or faces, number of faces containing something like this is going to be changed. So this has to be suitably modified immediately by the system, and that data has to be updated in the face table or edge table or vertex table, and only there with that data it is going to be displayed onto the display screen, right? So due to that there is this has to be calculated properly, right? Okay, so that is with regard to this Euler's operation in general. Okay, so the task required to modify the data in the data structure is used in the modeling system. So if it is a data structure file, okay, and this is going to be where it is going to be modified. So the import, it's important because the modeling function are basically implemented by bookkeeping operations. That is, this table has to be updated regularly whenever the modification is going to take place. So if they are going to make use of the brep file, because as we know there is csk file as well as the brep file. So in the brep file, uh, we shall first look into the brep file first. Okay, so in this we have data structures for shell, number of faces, the loop, edges, vertex, all these things are there. Okay, so when the operator is going to do the manipulation or is going to modify, okay, this is going to have certain it's going to have certain problems. So what is that? So the first thing that is going to have the problem is that in trying to handle it independently for each topology, right? And that is not entity, and that is not independent of others. So say for example, what they are trying to say is that if we have a cube, okay, and if we have a cube, and I'm going to split this particular face into two regions, okay, which was previously one face over here. Okay, now I'm going to draw one line, and this is going to be one face, this is going to be another face. So this has happened because of the operator or the user has drawn one edge. So what has happened? Number of faces present in this solid modeling has changed. Number of edges that is now present is also been changed, right? So just by making one line, it is not only that line or vertex is going to add up, but also subsequently interrelated data will also change. So thereby what Euler has proposed is that this particular formula. So whenever there is a change, okay, so where this formula is easy to calculate what can be the changes uh, that is there. So where V represent the number of edges, E represent the V represent number of vertices, E represents the number of edges, and F represents number of faces. Okay, and H represents number of pole loops. Okay, and then S represents number of shells, and P represents number of passages. So that can be through holes and so on. So they call it over here as the P, right? Okay, now with this formula, we can calculate, as I told, if we draw one edge, so what is going to be changing? Number of vertices are going to change, or number of faces are going to change. That can be easily uh, found out. So like that, so they've taken up an example over here where, so if you see over here, uh, what they have done is they've taken a cube within which there is one more hollow square hole that has been made. Okay, so here totally, if we see how many number of vertices will be there, we'll have 16 vertices because 8 corners for the cube and 8 corners for this hole, that is square hole that is present. Okay, number of faces will be 10. Okay, and similarly H value will be 2, S will be 1, and number of holes that is going to be there is going to be 1. So now when we substitute in this, it is going to be it is going to satisfy the equation. Okay, right. So now what and all we have over here is 1, 2, 3, 4, and 5 and 6. So out of these 6 entities, at least 5 should be known to us, right? So that the sixth one can be found out easily, right? Out of these 5, at least, out of the 6, at least 5 should be known. The second one is that what is going to happen is that uh, the second one is that it is not efficient to manipulate each topology entity separately. So if we start doing like this, then everything will not be automated, where the user only has to change all the data. So since they are interrelated, it is always better to have that the data is going to be automatically updated. So in most cases, addition or deletion of one means or changes in the other means, okay, will cause some problem. So it has to be updated. So as we see here, if you just draw one hole, then all the other data, number of faces, number of vertices, all these are going to change, right? Okay, right. So that is going to be a secondary conflict that is going to happen, as all these are interrelated to represent the data. I mean the image onto the screen. Okay, right. So yes, and okay. So now what they'll do is that okay. So it is thus helpful to disable to have operators that would manipulate topology entities in small group rather than individual. So it has to happen one by one. So even if some of you, I don't know if you have tried up, if you worked on hypermesh also, when we have any surface in hypermesh, and say for example we have done the meshing, and in some particular place there is a triangle, and we don't want that triangle to be there. When we modify this, subsequently the alternate regions related to that will also be modified automatically when we do in hypermesh. So that is what has been informed over here. So it will be changing in smaller groups rather than modifying only that particular single cell over here. So that makes it going to be helpful for each operator to handle simultaneously. Okay, and the entities will change the as a group as the solid is also going to be modified. Okay, right. So yes, and so that's how this Euler's formula is going to be used to uh, for the display as and when we make any changes in the system. So yes, that's what I informed just mentioned over here. It is shown. So previously it was a cube like this. So they have introduced one edge. So number of edges has been changed. Number of faces present for the same cube, though dimensions have not changed. Number of faces have also changed. Number of vertices has not changed, but right. So like this, it has to be done. So there is one simpler way where they do this, where they call it as make an edge and a loop. Okay, so they have made an edge and it forms one loop. Okay, make that is nothing but forming an enclosed diagram. Okay, enclosed like a triangle or a square, something like that. So it forms a loop where it does not have, as soon as I make one edge, that this is no more left open. It is again enclosed only. So a triangle is an enclosed diagram, right? So like that. Okay, right. So for this, there are certain shortcuts that they've given to understand. So one of them is what we have seen just now. Excuse, excuse me. So one of them is to make an edge and a loop, or kill an edge and a loop. That is nothing but make an edge is to draw a line, kill an edge is nothing but to delete a line. So if we have to make an edge, okay, which is previously like this, okay, if we draw one edge between the vertices, it is going to form one loop, okay, and a new edge has been created, right? But if we delete the same from a existing enclosed diagram like a triangle, any one of them, then one of the edges is going to be lost, and the connectivity between that vertices connecting that edge is also going to be lost. So that is what they call it as MEL, in short form, make edge loop or kill edge loop. Okay, right? So similarly over here it is for make edge. Okay, two vertices will have to be there, and the loop can also be will be coming into picture. So if we have a line that has to be created, two vertices are going to be generally going to come up, because for any line or arc there has to be at least two vertices in the picture, right? So similarly over here also it is there. So if we have make edge vertex, so if we have to make an if we have to make an edge from the very beginning, that is, as of now we have only a dot, that is only one vertex, and we have to create an edge or a line or an arc, then one more edge is being created, one edge has been created. Along with that, another vertex is also been created. So starting with one point, it has been transformed into an edge plus one point. So if we kill this, if we delete this line, even one of the point is also going to be lost. Okay, so that's how it has been done for even for the number of faces also, right? And for a zero length and for a peripheral loop also. So they are given short forms to this so that we can easily remember this, what is going to get added up and what is not going to be added up, so that these things can be easily edited in the Euler's formula. Right. Okay, so the next one is the Boolean operation. In the Boolean operation, yes, so Boolean operation is actually what we see onto the, when we do the solid modeling, CAD, using the CAD packages and all those things, it seems to be very easy to make use of the Boolean operation, but it's actually a difficult modeling function to be implemented, and but also at the same time, as you know, it is very much user friendly. So because it's a very much powerful modeling uh, tool that is always present in the modeling softwares, right? So yes, so what do we have over here in the Boolean operation is by performing union, intersection, and differences on any two solids, that is resulting in a data structure file. So where the data structure solids is going to be in the CSG tree format. Okay, right? So in that case, this is much more better to have. Okay, uh, so this can be, so here in CSV format, using a Boolean operation, it's easier to obtain by when compared to BREP files, when compared to BREP files. So in Boolean operations can be easily obtained by applying a Boolean operation in value of each space or voxels occupying the same space in two solids. So what is going to happen over here? Uh, so they need to calculate over here in the CSV file whether it is going to form another solid, which is either which is going to be represented in the form of zeros and ones. So which by this it is also called as the bitwise Boolean operation. Just by changing any data over there, what is the change in the bit structure is going to be observed, and based on that the Boolean operation is also subsequently going to change, because the register keys are going to change its values from 0 to 1 and 1 to 0, right? Okay, right. So yes, so we shall continue with that, because in most cases the BREP files are only used because the BREP file, as we know, is got a sufficient data to be stored when compared to the CSV file. So how to make use of BREP, I mean Boolean operation in a BREP file is the next thing that we'll be seeing here. So here BREP files results resulting solid to be retrieved from the B-reps of solid by applying the Boolean operations, which is also going to have one particular evaluation method, because it's not that easy to where the Boolean operation can easily fit onto the B-rep file. Right. So there are three steps that basically comes into picture for this process. Okay. So one of them, okay, so uh, so there's a figure over here. Let's see that. Okay, so yes, here we have one plane, a rectangle, and another plane, B. Okay, where both of these two is going to intersect in this particular portion, C, right? So this common area is called as the C region, which is the common area, the intersection portion. So this is another plane, this is one more plane. Okay, when both of these are to be combined using Boolean operations, it can be addition or subtraction and all those things. So after, say for example, if it has to be added up and brought into a new shape using these two, then how it is going to appear is that it has to appear like this, right? So that the common region is being lost. So if you are going to add it up, right? So how is this going to identify and remove only this particular region when we say add these two planes or add these two solids? Okay, right? So how does it take place, right? How does the system understand, or what is the algorithm written for this is what we'll have to. So for that to take place, there are three basic steps that it has to undergo, right? So what is that? We shall see one by one. So here we have applied Boolean operation has to be applied on face A and B. Resulting Boolean operation should be a face number C. So in this, what should happen? In the first step, all the edges of A and B edges obtaining by the intersection of two faces are collected from the edge pool. So in a BREP file, we have an edge table. So what are the edges in the rectangle or plane A, and what are the edges in the plane B? So that data, it is first going to take out that data, and then the pool includes all the edges as a subset, all edges of C as a subset. So wherever these common same edges are going to come into picture, it is going to take it as a subset called C. Okay, right. So in the next step, what is it going to do? Each edge in the edge pool is classified according to its relative location with respect to faces A and faces B. So as a result, it can be classified like this. So what does they say? Relevant location. We'll see here that. So whether the edges are going to be inside or on or outside face A. And similarly, the edges are going to be inside or on or outside face B. So what is this actually is that? So if you look over here, uh, we can see that this particular edge, this particular portion of the line of B is inside the A, in A of B, okay, in A, right? And similarly, this particular portion is also inside A only. But this portion of this rectangle, okay, this particular portion is in B but on A, actually from A, but it is inside the B region. And similarly over here, this part is belonging actually to the A rectangle, but now it is placed inside the B rectangle. So it is going to identify whether it is inside which plane, or is it this line is also going to be exactly over here only on the line or outside the line. So if you look at this particular portion of the line is outside. Okay, so that is what they have mentioned over here, outside A but on B, right? So this particular portion is now outside A. So this one is here. So here if you look, this edge is completely outside A, nowhere connected to the rectangle of A itself. So outside A, but it is this line, where does it actually belong to? It belongs to B rectangle, so on B, right? So this data is what is going to be captured first. So based on this data only, the next processing is going to occur. Okay, right. So yes, okay. So now it is going to take out that, okay, with respect to A rectangle, with respect to be rectangle also. Okay, and yes, next in this step number 3, the edges are collected, so they are grouped by a relative location, and specified Boolean operation is going to be applied. So based upon whether we want to add or subtract, subsequently that particular common features are going to be taken into picture. Okay, so one thing what happens is that we do not have to collect the edges that are in B, in A and in B for A union B. Okay, we don't need that for A union B, but we require it for A intersection B. And similarly, edges out of A and out of B, okay, have to be discarded for A intersection B, because for A intersection B, what do we need? We need which is the intersecting portion only. We don't need what is outside that portion. So all that data can be discarded. We don't need that for processing at all. So making use of the mathematical functions and taking into picture of this data, whether the both the lines are one within the other or the regions are one within the other for intersection. Based on that data that has been collected, the function is going to be carried out. Okay, right. So this approach is actually what we are seeing is for a 2D drawing, but the same thing can be applied for the 3D drawing also. That is for solid modeling, where when we have a cube or any other solid modeling, okay, and subsequently we want a cylinder to be merged with this, right? So that when combining these two, we get a diagram like this. So when we combine, we get a diagram like this, right? So using the Boolean operation. So here what happens is number of faces comes into picture, okay? But the same algorithm can be used, but it is very much difficult because it has to calculate for every edge, every vertex and all. So there was another person who has come out with the vertex neighborhood formula, like unlike the edge by edge approach. Okay, so in this algorithm, it takes care of the face by face approach. What are the common faces that if we have to add, which is the common face that is going to come into picture? If we are going to subtract, which are those common features, whether it's inside, whether the faces are inside or outside, right? So like that, face representation data are taken and the Boolean operations are performed in solid modeling. So the only change in the algorithm is only with respect to from edge by edge, it is going to be changed to face by face approach for solid modeling. Yes. Okay. So okay. So yes. So next one is the non-manifold modeling systems. So what is this non-manifold modeling systems, um, and what is manifold modeling system? We shall first see what is manifold modeling systems. So in a manifold modeling system, in a solid modeling system allows a user to create a shape having an enclosed volume or a manifold system in mathematical terminology. So whenever we create any solid modeling, it is going to be having an enclosed volume. It is called as a manifold system. Okay, and so this does not allow the non-manifold conditions. That means, so when we have when we go to solid modeling, what we can do is that we can always do a solid modeling something like this, a cube or a cylinder or a cone. So all these are enclosed volume. Now I want this particular rectangle to be placed over here. So previously it was a cube. Now I want a rectangle to be placed over here, that's all. But now this rectangle is not a solid modeling at all, because it has only two dimensions, the length and the width, but no thickness at all, right? So this is a non-manifold structure where this will not be allowed to be done on a purely solid module package. Okay, so when we go to any modeling packages, there is option where we have to select the uh, modeling system that we want, whether we want 2D drawing or sheet metal or part drawing or assembly drawing, right? So when we go to solid modeling, part drawing, it is nothing but solid modeling. So we can create solids, but we cannot create and finish the modeling just by having a any kind of 2D representational data, right? So that is not at all allowed. So anything like this which is there having does not have the third dimension is a non-manifold system, okay, which is a non-modeling system. So there are situations where both these have to exist in the same module itself, okay, on the same platform, okay. So that is needed. So but in a solid in a solid part modeling, we don't have this option, right? So only manifold data or creating solid modelings are only allowed. So yes, okay. So yes, that is what has been mentioned over here in this particular portion. So let's go on to the next thing. So yes, so when we do some solid modelings, examples of non-manifolds are something like this. So we may have to have two uh, triangular prisms where there is this common vertex coming into picture, which is actually a two dimension, or it can be only both of these can be joined at one particular point having one vertex, or it can have, just as I mentioned just now, this is a solid modeling, but these two are a 2D drawing, so which has to be combined to a solid modeling when we do it on the system, right? So, and we would have seen this especially when architects use this, okay, where there will not be any thickness for this. There will not be any thickness for this. If we have to do the same thing on a solid modeling uh, module, then we have to make use of thin sections, and there will be giving what is the thickness of this, right? So here we don't need to give that. So in that situation, it is going to become a non-manifold structure. So there is every time that this is going to come into picture. So why this is going to happen is that for in a non-manifold model, given a point on a surface need not necessarily be a flat, or neighborhood point need not be to a two-dimensional disk as shown in the above figures, right? So we can have in some places, as just seen, uh, logically two-dimensional surfaces are going to be there, right? So now what is going to happen with this? Uh, Now say for example, a designer wants to make a design a plastic container, okay, and might start with a model just as a rough sketch, okay, without considering what is the thickness it should be. So just like this above diagram, we will only draw this. We will not give the thickness as of now. Okay, so in that case, the solid packages will not allow. Okay, so similarly, naturally, initial designs for structure, okay, and composed of solid blocks, holding plate, and all these are going to come into picture. So initially, without considering um, these things, is what is going to be done in the industries also whenever they're going to come up with the uh, initial drawing. So nowadays, even the initial sketches are being done using the system. Okay, so there need to be a platform for that. Okay, so that's nothing but the abstract of mixed dimension. So it will have not a fixed dimension. Some places dimensions should have been mentioned. Some places no dimension should have been mentioned. And similarly, uh, uh, thickness will not be mentioned at all, right? So it will be only a at some regions we will have the thickness, some regions will not have any thickness to be mentioned. So that is called as the abstract of mixed dimension, the abstract models, okay, which is not actually the complete. So it will be a mixture of all solid as well as 2D drawings like lamina plates and so on. So various analytical tools can be applied to verify the design at each stage and for Yeah, and for each design process. So this raw data is going to be utilized by different teams, that is by the modeling team and the analysis team. And based on that, they are going to suitably give the thickness or any other dimensional data and further process it on. So this raw data is what is going to be initially used. Okay. So for this, this is one respect with respect to the it is actually with respect to the modeling. So they can change the data, I mean, give the thickness wherever it is being missing. So for every place, as of now, one say, for example, this drawing is going to go to the uh, modeling team, then they start giving the thickness for every lamina that is present over here. Okay, right? So what can be the thickness? What should be the material be made up of? All this they are going to choose depending upon uh, the application. Okay, and as per the customer requirements. So this is okay, but when it comes to the design phase, say for example, we have one type of uh, model like this. Okay, where let us assume that this has got very small thickness of 2 mm, but this is a solid model. Okay, this is a solid cube, and these two is only a lamina having a very thin material, or maybe 2 mm thickness. Let us assume. Okay. Right. So in this case, when the design person goes for analysis, uh, what is going to happen is that now, as we all know, whenever we do any type of analysis, we have to use suitable mesh elements. So here we can use solid mesh elements since it is a solid. Okay, but we cannot use the same solid mesh over here also. The data is going to be different. Our analysis results will vary, right? So because one is a manifold model, the other one is a non-manifold model. So we cannot use the same mesh type over here. Okay, since it's got a very small thickness. So for this to obtain better results and accurate values, we have to go for shell elements over here, as because the thickness is very less in the non-manifold portions, right? So this flexibility has to be there. So we cannot always expect that whenever we do any analysis, it is always going to be only with respect to one type of mesh element. So in the same model, many different types of elements has to be chosen, right? Mesh elements have to be chosen. So one way of identifying this is based upon the type of model that is going to be there, whether it's going to be a solid model or the other portions are going to be made up of thin sections. So according to the varieties, the mesh elements have to be chosen, right? So, right. Um, yes. Okay. Yes. So that is what is actually mentioned over here. So when we take the abstract model at each design process, we need to perform the modeling and then we need to perform the finite element analysis on a component. So they will, depending upon that, if it's a thin section, they'll make use of shell elements on the abstract shape, because it is still in the process of designing only, and rather than generating a solid mesh that will be used, right? Rather than a solid mesh that will be used, because there is not much thickness for this. Okay, so more abstract models, as an most of the abstract models require intermediate results in the design process, and the representations of the composed mix of one or two and three dimensional elements is what has been indicated as I showed in the previous diagram. Okay, and for this, the modeling system that supports the representation of such schemes need to be transformed between one, two, and three dimensional geometrical entities. So it must be able to transform from one form to another form, so that when they're combined, there is not going to be any type of problem. So this system allows a unified representation of wireframe, then surface modeling, solid modeling, cellular models simultaneously in the same modeling environment, while increasing the respectable range of models beyond individual. That is making, say for example over here what they're trying to say is that if we take up a car body, okay, and we are going to do the impact test, then the engine is actually a solid block, then the car surface panels are actually thin sections. So all these things have to be brought onto one window, right? One window, and all these elements are going to be different. But when we are going to do the impact test, then all these have to be meshed up, and this mesh has to be linked also, because one-to-one components are linked in one place or the other place. So all this has to be uh, on the same window, because initially when we learn, the solid modeling package is on a different set, the other package, the surface modeling, is a different set, so it has to be unified, otherwise we cannot do for further analysis. That is what is actually uh, being mentioned. That is the plus point of this uh, of this non-manifold regions in this picture, right? Okay, so yes, we'll stop here for today. Yeah.